This is joint work with Michael Bender from Stony Brook, Dzejla Medjedovic, who's in Sarajevo. I'm trying to remove this. Oh, good. Dzejla Medjedovic, who's from Sarajevo, Pablo Montes, who's now at Google, and I should remove that. And Kostas, who's in Thessaloniki, Greece. So the title is Batch Predecessor and Sorting. So the two problems that we study are batch predecessor and sorting. Sorting, everyone knows. What is batch predecessor? Well, what is predecessor? You're given an ordered set, you get a query, and you want to find the predecessor of that query in the ordered set. Batch just means instead of getting one query, you get a batch of queries. So these are the two problems that we study. And I'm guessing not many people would have seen the size priced information or external memory models. So in the talk, I'll describe what the price information setting is. And then I'll just briefly describe what the external memory setting is. And then I'll talk about our results on these two problems. So what's the price information setting, right? So this was basically developed when you have a bunch of inputs and you can't really, figure out all of them at the same time, like it costs to probe an input. So let's say you have some target piece of information, right? So you have a decision rule on some unknown variables. And so your decision rule looks like if analyst A values Microsoft at X dollars or analyst B values Tesla at Y dollars. So in order to ask analyst A and analyst B what these values are, it costs you something. And you could have a longer complicated. And if analyst C values Google at W, D values Apple at, this should be Z, then give all your Bitcoins to Jeff and move to Brazil. So you have some sort of weird decision rule. And the question is, you don't need to ask all the analysts in order to evaluate this decision rule. You can probably ask a subset of them. So that's the setting of price information where you want to gather information either as fast or as cheaply as possible. Okay. And this has plenty of domains for application, software, research papers, and basically corporate and finance areas. So the main paper studying this was by Charikar et al. In Stock 2000. And they basically said, let's say you have a function f over some n inputs. Each input has a price. And we want to minimize the total cost required to evaluate the function. So you can query the input sequentially. And they did a competitive analysis, which is comparing to the cost of the cheapest proof. So now their problem was very general. And next, Gupta et al. And Fox studied sorting and selection. And so they studied sorting, where each comparison has an associated cost. So not all the cost, not all the comparison costs are uniform. You have a associated cost. And they studied the setting, for example, let's say you're sorting databases by a costly proxy in some unknown order. So you don't know so basically there's an oracle that's comparing, you don't know what the order is, and you have pretty large keys. What they showed was that if the comparison costs are arbitrary, then you can't really get good approximation ratios. By approximation ratios, I mean this competitive ratio. But they also showed that if the cost is well behaved, so for example, if the cost to compare two databases is the sum of the sizes of the databases, or it's the product, which means comparing all pairs, then algorithms with good competitive ratios exist. And building upon this structured thing, so Angelo et al. In Latin in 2008 proved for the other setting, when the costs are completely independently random, then also you can get good competitive ratios. So what we will be focusing on are what I've highlighted in red here. So we want to study sorting mainly in this priced information setting. But notice that, I mean, when you were talking about databases, these are big. And the traditional work has been done in RAM, right? But if databases are large, they won't fit in memory. So we believe a good setting to study this would be the IO model. And so in the IO model, the IO model was developed by Agarwal and Witter. So I'll just briefly describe in a slide what the IO model or the external memory model is. It's also called the DAM model, for disk access model. It's a model of hardware aimed at massive data sets. So basically what's happening is CPU computation is free, and transferring data from your external storage to your main memory is the main bottleneck. So in this model, your main memory has size M. So think of it as an array of M length. And this array is arranged in M over B blocks. And each block holds B words. So in the external memory model, we have these two parameters, M and B. M is the size of your main memory. B is the size of a block, how much stuff you can bring from external memory into main memory in one transfer. So external memory has data stored in blocks, again, of size B. And an I/O, which is for input-output, consists of reading or writing a block from external memory or writing it from main memory to external memory. And then the cost of an algorithm is measured in how many transfers or how many I/Os you do. Whatever you do inside your main memory is free in this external memory model. So coming back to our problem, right? So where they were studying the priced information setting, where for example, the cost to compare two databases is proportional to the sum, right? The sum of their sizes. But in the external memory setting, this sort of naturally comes into play, because if you have a large element, then it'll take you longer to bring it into your memory. So the larger elements, the fewer can fit in an I/O. So for example, if an object has length W, which is at most B, then you can fit up to B over W such objects in one I/O. And as I mentioned, the traditional algorithms, they only consider the case where W is 1, right? So you just have unit size. So you say you can fit B things in a block. For us, we'll be considering objects which are not length just 1. On the other hand, you could have very large objects. We're talking about databases here, so there's no reason that they cannot be larger than a block. So if you have an object who's larger than a block, then you will need multiple blocks. You will need W over B I/Os to bring it in or write it out. And I'm missing like a ceiling here, because W over B need not be an integer, but I'll be missing those ceilings all throughout the talk. So you could have elements of length W, and you will need W over B I/Os to bring one such element into memory. So now, why is this different from the traditional external memory algorithms? Well, external memory algorithms, basically, they make advantage of parallelism. But now if you have a large element, when you bring it into RAM, it will also displace a lot of short elements from RAM. So your level of parallelism will reduce. So hopefully the size price setting and the external memory setting is roughly clear. And I can now state our problem. So it's a very simple looking problem, just sorting with two types. So you have two types of keys, let's say, to sort. You have n red keys and n blue keys. Your red keys have unit size. So B of them fit in one block. And your blue keys have size W, right? W is greater than 1, could be greater than B, could be less than B, it could be anything. All keys are indivisible. So in order to compare a key to any other key, you have to bring the key in its entirety from external memory into main memory. Right? And so all the objects, all the red and blue keys are in external memory at the beginning, and you're supposed to sort them and write them out to external memory at the end. So now the question is, what does an I/O efficient algorithm for this problem look like? And it's a very simple generalization of the usual one size sorting problem in external memory. But turns out this one is actually sort of tricky. I mean, it looks simple, but it's not as straightforward. And in fact, the I/O efficient algorithm, it actually depends on how these red and blue keys are sort of interleaved in the final sorted order. So let's take a short detour to RAM, right? So usually the setting that we are familiar with, to see a similar problem. So here's the similar problem in RAM. So again, you have two types of keys, n red and blue. And since you have red and blue keys, you can have three types of comparisons, right? So let's say a red-red comparison costs A, comparing a red key to a blue key costs B, and comparing two blue keys costs C. Okay. And now I want a sorting algorithm that minimizes the total cost. So I'll show in a moment how for general values of A, B, and C, I mean, this problem is actually pretty technical. But the important thing for us is that we really care about the case A less than B less than C. Because in external memory, we'll have these small keys, right, which can be compared or can give you a better comparison. You can bring many small keys into memory, or you can compare a small key to a large key, which won't give you as much information. Or you can compare two large keys, which, again, per I/O gives you the least information. So we are really interested in this case. And in general, for all values of A, B, and C, if you think of the case when B is 1, so a red-blue comparison costs 1, but a red-red or a blue-blue comparison costs infinite. So basically, you're not allowed red-red or blue-blue comparisons. And this is basically the nuts and bolts problem, which already had, I mean, it had a bit of research done on it. So just this one sample point is a pretty research problem. So in all generality, solving for all values of A, B, and C will require some work. But as I mentioned, for the purposes of our external memory problem, we care about the case A less than B less than C. And for this case, the important observation, which I sort of alluded to earlier, is that interleaving matters. So again, if you consider the stripes in the final sorted order. So let's say in the final sorted order, all the red keys come first, and then all the blue keys come. Then you kind of know that you have to sort the red keys, you have to sort the blue keys, and concatenating them is basically optimal. On the other hand, if this is your final sorted order, so you have some red keys, blue keys, red keys, blue keys, then it turns out that the best thing to do in if A is less than B is less than C is you sort the red keys, then you solve a batch predecessor problem. So you search for the blue keys in the set of red keys, and then you sort the blue stripes that you obtain. So in this setting, right, this is the kind of algorithm that is optimal. And here it naturally shows how batch predecessor problem appears sort of embedded inside the sorting problem. So coming back to our external memory problem. So first of all, how do you sort unit-sized elements in external memory? Well, the algorithm is basically a merge sort, but you have more parallelism. And the I/O complexity to sort n keys is this. Right? So it's n over b log base m over b of n over b. Basically, you're doing an m over b way multi-sort. And I'll show you a lower bound later. So this is tight. Now, again, as I mentioned, we have two types of keys, small keys and large keys. So here are the parameters of our problem. M and B are as before, the external memory parameters, size of main memory and size of a block. S will be the number of red keys. And since the red keys are unit size, this is also their volume. L will be the total volume of the blue keys. So the blue keys are the large keys, where each key is size W. And so there'll be L divided by W, many blue keys, right? L is the total size of the blue keys. And we want interleaving sensitive bound. So as I mentioned, right, it depends on how these red keys and blue keys are interleaved. So we have these two other parameters, K, which is the number of stripes. So how many times the blue keys, are cut off by the red keys. And Li will be the volume of the ith blue stripe. So in these parameters, we want algorithms that are optimal for any instance. We're looking sort of for instance optimal algorithms in these parameters. So our first result is we show how sorting is related to the batch predecessor problem. So we say that the complexity of sorting the two keys, the problem that I mentioned, is a red term, which involves sort of sorting the short keys, then this batch predecessor problem, and then sorting sort of the blue stripes. So, I mean, it's sort of straightforward to see that this is an upper bound. What is not as straightforward to see is that this is also a lower bound. So we prove that the first term, the third term, and the second problem are also lower bounds to the sorting problem. So we get this theta here. And what now we have reduced the problem of sorting is to study the complexity of this PLE. PLE stands for place long elements, which is the associated batch predecessor problem that I was talking about. So sorting in this model basically reduces to a batch predecessor problem. Again, S is the set of short keys, L is the set of long keys. So how do we solve this problem? So actually, you can have two types of candidates. They are sort of analogous to BFS and DFS. So the first one is a 2-tree DFS. So what I mean by 2-tree DFS, so you have your set of S of red keys, they are sorted. So build a B tree on them. B tree is a tree with fan out B. And then what basically you do is, whenever a blue element goes down this set of this tree on the red keys, it discovers a stripe, and we call the bordering red keys of that stripe. We put them in a set S border, and we also build a B tree on this S border. And then what we do is, basically any blue key, it first goes through this S border, right? So these are the already discovered stripes. And if a blue key goes down in an already discovered stripe, then great. It only incurs a cost log base B of K, because basically there's only order K border elements because there's order K stripes. On the other hand, It could happen that a blue key is discovering a new stripe, in which case when it goes down the small tree, it won't give us any information, and then we send it down the large tree. So then you get a k-log base P of S. So this is the first candidate algorithm. And this actually works when the keys are very large, when the large keys are very large. Because notice that once you bring a blue element in memory, you basically flush it down the tree completely. The second candidate is sort of a BFS, which is simpler. It is you build a tree with theta m fan out, and then you flush all the large elements through all layers of the tree. Right. So this is the running time for the second algorithm. And which is better? So I kind of mentioned that BFS is better when elements are very large, when the large elements are very large, because they're only brought in memory once. And BFS is better if they're not that large. There's a value of how large they are when this transition occurs. And so we have an algorithm, right, which is the complexity is the minimum of these two. So we have an upper bound. So now this is a weird upper bound, is the minimum of two terms. And what about lower bounds? Do they also exhibit this sort of dichotomy? And this is the sort of the hard technical part of the paper. And I won't be going into the details, but I'll just mention why this is sort of challenging. So what is the lower bound for unit size keys, right? So if you have n unit size keys, first you can assume that they're all sorted in n over b IOs. And then the number of permutations that you need to achieve is n factorial divided by the number of permutations that you've already achieved by sorting the blocks. And then you talk about fan out, right? So in one IO, how many permutations can you achieve? And it turns out it's m choose b. And you take the log and you get your lower bound. And now the main thing here is that the fan out is uniform, right? There's only one type of IO. And also the adversary sort of has no restrictions. You can make your answers however you want. For us, the traditional argument won't work. As I mentioned, the fan out can be very different. And it's basically, so I'll go through the second challenge in a moment, but the naive bound here for fan outs are not tight. And so that's the first thing, because we have two types of keys, fan outs are different. The second reason is we want interleaving sensitive bounds, as I mentioned. We want bounds that depends on k. So the adversary cannot really give whatever answer it wants, right? Its bound has to depend on k. So its answers must arrive at an instance with k stripes. And the third reason, which is sort of more technical, is this is a problem that is embedded in sorting. And so we don't really know how much preprocessing to allow it, because we don't know what the first and the third steps did. But basically, we solve these challenges, and we get a lower bound on PLE, which is also turns out to be a minimum of two types of things, which shows the same dichotomy as our upper bound. And so basically what we have shown is we considered the sorting a problem with size price information in external memory. We show how this batch predecessor problem is important, and we develop interleaving sensitive upper and lower bounds that depend on the distribution of keys. Our bounds are tight for a wide range of parameters, but there's a gap, and tightening that is one of the open problems. And this will require resolving the complexity as a subproblem, or complexity of this batch predecessor as a subproblem of sorting. But again, this was a simple toy problem, right? So what if you have multiple sizes, multiple types of keys? The algorithm sort of generalized, but the lower bound do not, they won't be tight straightforwardly. And again, we just considered sorting, but you could consider other problems in this model also. And that'll be all. Thank you for listening.